Embarking from the aftermath of the Big Bang, a monumental explosion that occurred approximately 13.8 billion years ago, we venture into an era where the universe was in its infancy, teeming with high temperatures and dense energy. This initial burst set the stage for the universe's formation, marking the beginning of space and time as we understand them. In the fleeting moments following the Big Bang, the universe was an incredibly hot and dense point. Within fractions of a second, it began expanding at an exponential rate, cooling as it did so, allowing for the formation of the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces. As the universe expanded and cooled, conditions became ripe for the creation of the first subatomic particles, such as quarks and electrons. These particles, born out of the energy from the Big Bang, eventually combined to form protons and neutrons. The universe, however, was still too hot for these protons and neutrons to combine into atoms. It wasn't until about 380,000 years after the Big Bang, as the universe continued to cool, that protons and neutrons began to combine to form the nuclei of the simplest elements, hydrogen and helium, through a process known as nucleosynthesis. Hydrogen, the most abundant element in the universe, and helium, the second most abundant, were the primary products of this early nucleosynthesis. Trace amounts of lithium were also produced during this period. The creation of these elements set the foundation for the complex chemistry that would eventually lead to the formation of stars, galaxies, and planets. As the universe continued to expand and cool, gravity began to pull together clouds of hydrogen and helium gas, leading to the formation of the first stars. These first stars played a crucial role in the evolution of the universe. Through nuclear fusion in their cores, they forged heavier elements such as carbon, oxygen, and iron. The life cycles of these stars, including their eventual explosion as supernovae, dispersed these heavier elements into space, seeding the cosmos with the ingredients necessary for the formation of new stars, planets, and eventually, life itself. The cosmic microwave background radiation, or CMB, is a faint glow that permeates the universe, offering a snapshot of the cosmos a mere 380,000 years after the Big Bang. This glow is not just a relic of the past, but a treasure trove of insights into the early universe, its composition, and its evolution. The CMB's discovery in the 1960s was a pivotal moment in astrophysics, providing strong evidence for the Big Bang theory. This radiation is the afterglow of the universe's explosive birth, stretched and cooled over billions of years as the cosmos expanded. Its uniformity and slight variations tell us a compelling story about the universe's infancy. One of the most fascinating aspects of the CMB is its astonishing uniformity. Across vast expanses of space, the temperature of this radiation is incredibly consistent, about 2.7 Kelvin or minus 270.45 degrees Celsius, with minuscule fluctuations. These minute temperature variations are crucial for cosmologists because they represent the seeds from which galaxies, stars, and eventually planets formed. Essentially, these fluctuations in density and temperature underpin the large-scale structure of the universe we observe today. The CMB also serves as a profound probe into the composition of the early universe. By studying its light, scientists can infer the universe's makeup at that time, revealing a cosmos filled predominantly with hydrogen and helium, the simplest and most abundant elements. This elemental composition supports theories of nucleosynthesis, predicting how the first elements formed in the universe's nascent moments. The polarization of the CMB light, akin to the way certain sunglasses can block out glare by aligning light waves, offers additional clues about the early universe. Another intriguing insight from the CMB is the glimpse it offers into the nature of dark matter and dark energy, mysterious components that constitute most of the universe's mass-energy content. The way CMB radiation is scattered and its interaction with matter over cosmic timescales helps cosmologists map out the influence of dark matter in clumping matter together and the role of dark energy in accelerating the universe's expansion. In the wake of the Big Bang, the universe was a formless expanse of energy, primed to evolve into the structured cosmos we observe today. This transition from chaos to order was governed by the emergence and shaping of the laws of physics, fundamental principles that dictate the behavior of the universe. Initially, in the universe's first moments, temperatures were unimaginably high, and the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. As the universe cooled, these forces began to separate, a process pivotal to the formation of the cosmos as we know it. The first to split was the strong nuclear force, responsible for holding the nuclei of atoms together. This separation set the stage for the formation of the first subatomic particles, including quarks and electrons, mere fractions of a second after the Big Bang. As the universe continued to expand and cool, quarks coalesced to form protons and neutrons, the building blocks of atoms. This period, known as the quark epoch, was crucial for determining the amount and types of matter that would dominate the universe. Following this, the universe entered the electro-weak epoch, where the electromagnetic and weak nuclear forces distinguished themselves. This differentiation was vital for the creation of various types of particles and antiparticles, and for the processes that led to the predominance of matter over antimatter in the universe. Without this asymmetry, matter and antimatter would have annihilated each other, leaving the universe devoid of the galaxies, stars, and planets we see today. As the universe aged, it cooled sufficiently for the first atoms to form, a phase known as recombination, occurring around 380,000 years after the Big Bang. This was a pivotal moment, as it allowed photons, particles of light, to travel freely for the first time, creating the cosmic microwave background radiation, a snapshot of the universe at that time. The laws of physics, particularly electromagnetism, played a crucial role in this process, dictating how electrons and nuclei combine to form neutral atoms. Gravity, the weakest but most far-reaching force, began to sculpt the large-scale structure of the universe during this period. Regions slightly denser than their surroundings began to collapse under their own gravity, forming the first stars and galaxies. This gravitational clustering is a process that continues to shape the cosmos, driving the formation of galaxy clusters and superclusters. Over billions of years, the interplay of these forces under the laws of physics facilitated the evolution of the universe from a hot, dense state to the vast and varied cosmos we observe today. Elements formed in the hearts of stars were scattered into space by supernovae, seeding the cosmos with the building blocks for new stars, planets, and eventually life. The laws of physics, emergent in the aftermath of the Big Bang, not only dictated the creation and behavior of the universe's fundamental particles, but also guided the evolution of the cosmos from simplicity to complexity. As we delve deeper into the mysteries of the cosmos, the process of galaxy formation and evolution stands as a cornerstone of modern astrophysics, offering a window into the dynamic ballet of matter under the influence of gravity in an expanding universe. This narrative unfolds over billions of years, tracing back to the subtle fluctuations in the density of matter shortly after the Big Bang, which we've seen imprinted in the cosmic microwave background radiation. The story begins in the primordial soup of the early universe, a nearly uniform field peppered with slight overdensities. These overdensities, though minuscule, were the seeds of all future structures in the universe. Under the relentless pull of gravity, regions of higher density began to attract more matter, growing increasingly larger and denser. This gravitational accretion was the first step in the long journey of galaxy formation. As these regions pulled in more gas and dark matter, a mysterious form of matter that does not emit, absorb, or reflect light but exerts gravitational effects on visible matter, they began to collapse under their own gravity. This collapse led to the formation of dark matter halos, invisible scaffolds around which visible matter could clump together. Within these dark matter halos, gas clouds continued to collapse, heating up as they densified, until the conditions became ripe for the birth of stars. This marked the emergence of the first galaxies, simple and small compared to the vast spiral and elliptical galaxies we observe today. Over time, these early galaxies began to evolve and interact. Some merged, pooling their stars and gas to form larger galaxies, while others were torn apart by gravitational forces. This era of cosmic evolution was chaotic, marked by frequent collisions that spurred bursts of star formation, known as starbursts, which shaped the galaxy's structures and compositions. Galaxy evolution is also a tale of internal change. Stars within galaxies live their lives on timescales ranging from millions to billions of years, depending on their masses. Massive stars burn through their nuclear fuel rapidly, ending their lives in supernova explosions that seed the galaxy with heavier elements. These elements, in turn, become the building blocks of new stars and planets, enriching the galaxy and influencing future generations of stars. Meanwhile, the supermassive black holes that lurk at the centers of most, if not all, large galaxies also play a crucial role in shaping their host galaxies. As these black holes accrete matter, they can emit vast amounts of energy, influencing star formation across the galaxy. Through these processes, galaxies grow and evolve, their shapes and sizes reflecting their histories of formation, interaction, and internal processes. Spiral galaxies, with their rotating disks and spiral arms, elliptical galaxies, ranging from nearly spherical to elongated ovals, and irregular galaxies with no distinct shape, all tell stories of their origins and the dynamic universe in which they reside. As we explore the cosmos, supermassive black holes emerge as cosmic architects, exerting a profound influence on the galaxies they inhabit. Lurking at the heart of nearly every large galaxy, these colossal entities, with masses ranging from millions to billions of times that of our Sun, play a key role in shaping the evolution and characteristics of galaxies. Supermassive black holes are not just cosmic oddities, they are central players in the galactic narrative. Their gravitational pull can dictate the motion of stars and gas clouds within a galaxy, influencing its overall structure and dynamics. But their influence extends beyond mere gravitational sway. As material spirals into a supermassive black hole, it heats up and emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays. This radiation can have far-reaching effects on the galaxy's environment. One of the most dramatic impacts of supermassive black holes is their role in regulating star formation within galaxies. The process, known as feedback, occurs when the energy released by the black hole as it accretes matter heats up and disperses the surrounding gas clouds that would otherwise collapse to form new stars. This feedback mechanism can quench star formation, effectively halting the growth of the galaxy. It's a delicate balance. Too much activity from the black hole can blow away the galaxy's gas, starving it of the material needed for future stars, while too little can lead to unchecked star formation, dramatically altering the galaxy's character. The interaction between supermassive black holes and their host galaxies is a dynamic dance. The growth of these black holes is closely linked to the evolution of their galaxies. Observations suggest a correlation between the mass of a supermassive black hole and the properties of its host galaxy's bulge, the dense group of stars at the galaxy's center. This relationship implies that the growth of black holes and galaxies is interconnected, possibly through cycles of gas accretion and star formation regulated by the black hole's feedback. In addition to their role in regulating star formation, supermassive black holes can also drive the formation of galactic structures. For example, jets of material ejected at near-light speeds from the poles of actively accreting black holes can carve out vast cavities in the intergalactic medium, influencing the distribution of gas and the formation of galaxy clusters. Supermassive black holes also contribute to the cosmic ecosystem through their dramatic end-of-life events. When galaxies merge, a common occurrence in the cosmic history, their central black holes can eventually collide and merge, releasing vast amounts of energy in the form of gravitational waves. These ripples in the fabric of space-time can provide insights into the fundamental laws of physics and the violent processes at the heart of galaxy evolution. Let us talk a bit about stars. The life cycle of a star is a story of transformation, a journey that not only shapes the destiny of the star itself, but also plays a pivotal role in the creation of elements, the building blocks of the universe. This cycle begins in the cold, dark clouds of interstellar gas and dust, where the seeds of stars lie waiting for the spark of creation. The first stage in the life cycle of a star is its birth, which occurs in nebulae, immense clouds of gas and dust. Within these nebulae, regions of higher density, aided by the gravitational pull of existing matter, begin to collapse under their own gravity. As the gas clumps together, it heats up, and when the core of this collapsing cloud reaches a sufficient density and temperature, nuclear fusion ignites. This fusion process marks the birth of a new star, converting hydrogen into helium and releasing energy in the form of light and heat. This is how a star enters the main sequence phase of its life, a period of stability where it spends most of its existence balancing the outward pressure of nuclear fusion with the inward pull of gravity. The next stages in a star's life depend on its mass. Medium-sized stars like our Sun will swell into red giants as they exhaust their hydrogen fuel and begin to fuse helium into heavier elements like carbon and oxygen. Eventually, these stars shed their outer layers into space, creating beautiful objects known as planetary nebulae. What remains is the core, which collapses into a white dwarf, a dense, hot remnant that slowly cools and fades over billions of years. For more massive stars, the journey is even more dramatic. After burning through their initial hydrogen, they progress to fusing heavier elements, ultimately leading to iron in their cores. Fusion stops at iron because fusing iron consumes more energy than it releases, leading to a catastrophic collapse of the star's core. This collapse triggers a supernova explosion, an event so powerful it can briefly outshine an entire galaxy. Supernovae are crucial for element formation, as they produce and scatter many of the heavier elements, beyond iron, throughout the cosmos. The remnants of these explosions can form either a neutron star, an incredibly dense object composed mostly of neutrons, or if the star was sufficiently massive, a black hole, a point in space where gravity is so strong that not even light can escape. Stars, through their life cycles, are the universe's forges, creating and distributing the elements that make up worlds and life itself. Every atom of carbon, oxygen, and iron in our bodies was formed in the heart of a star or in the fiery blast of a supernova, linking us intimately to the cosmos. Supernovae, neutron stars, and black holes represent some of the most dramatic and significant phenomena, each playing a unique role in the universe's evolution and in our understanding of physics. These celestial events and objects are not only fascinating in their own right, but also crucial for the synthesis of elements and the structure of the cosmos. Supernovae are the spectacularly explosive deaths of stars, events so bright they can momentarily outshine entire galaxies. They occur in two main scenarios, either at the end of a massive star's life when its core collapses under the force of its own gravity, or through the accumulation of material by a white dwarf from a companion star, leading it to exceed a critical mass and undergo a thermonuclear explosion. Supernovae play a critical role in the cosmos by dispersing elements heavier than iron into space. These elements, forged in the heart of stars or during the supernova explosion itself, are essential for the creation of planets and life. The energy released by supernovae also influences the structure of the surrounding interstellar medium, triggering star formation in some regions while dispersing gas and dust in others. Neutron stars are one of the possible remnants of supernovae explosions, formed when the core of a massive star collapses to such an extent that protons and electrons combine to form neutrons. These objects are incredibly dense, with a mass comparable to that of the Sun, but packed into a sphere only about 20 kilometers in diameter. Neutron stars possess intense gravitational and magnetic fields, with some emitting regular pulses of radiation as pulsars. These pulsars serve as cosmic lighthouses and have been used by astronomers to probe the universe's properties, including testing theories of gravity and measuring cosmic distances. Black holes, the most mysterious of these cosmic phenomena, form when the core of a supermassive star collapses under its gravity, creating a point in space where the gravitational pull is so strong that not even light can escape. Their existence was predicted by Einstein's theory of general relativity, and they have been the subject of intense study ever since. Black holes play a significant role in the dynamics of galaxies. Supermassive black holes at the centers of galaxies regulate star formation and galaxy evolution through their gravitational influence and the energetic processes associated with accretion of matter. The significance of supernovae, neutron stars, and black holes extends beyond their role in cosmic element synthesis and structure formation. They are natural laboratories for extreme physics, allowing scientists to study conditions of gravity, density, and energy that are unattainable on Earth. The observation and modeling of these phenomena have led to profound insights into the nature of matter, space, and time. The formation of planetary systems around stars is a captivating chapter in the cosmic narrative, revealing how the swirling clouds of gas and dust coalesce into the diverse worlds that orbit our universe's countless stars. This process, while complex, begins with the collapse of a molecular cloud, much like the birth of stars themselves. Within these vast clouds, pockets of increased density, perhaps nudged by the shockwave from a nearby supernova, begin to collapse under their own gravity, forming a rotating disk of gas and dust around a new central star. This star, fueled by nuclear fusion, lights up its corner of the cosmos, while the material in the surrounding disk begins the intricate dance of planet formation. Over time, particles within the disk collide and stick together, forming clumps that grow into planetesimals, the building blocks of planets. Through a process of accretion, these planetesimals continue to collide and merge, growing into protoplanets. The inner part of the disk, where it is hotter, tends to form rocky planets like Earth and Mars. In contrast, the outer regions, where it's cold enough for ice to form, give rise to gas giants and icy worlds. But the journey from a swirling disk of debris to a bustling planetary system is influenced by several factors, not least of which is the central star's properties. Its mass, luminosity, and magnetic activity can significantly impact the formation process and the eventual composition of the planetary system. Additionally, interactions between emerging planets can lead to dynamic changes, with some being ejected from the system or colliding with others to form larger bodies. When considering what makes a planet habitable, the concept of the habitable zone, or the Goldilocks zone, comes to the forefront. This zone is the range of distances from a star where conditions might be just right, not too hot and not too cold, for liquid water to exist on a planet's surface, a crucial factor for life as we know it. However, being in the habitable zone is just one piece of the puzzle. A planet's atmosphere and magnetic field can also play critical roles in maintaining surface conditions conducive to life. An atmosphere can regulate temperature, protect the surface from harmful radiation, and provide essential elements for life, while a magnetic field can shield the planet from stellar winds, preserving its atmosphere over time. The planet's composition, geological activity, and the presence of water in liquid form are essential factors that contribute to its habitability. Geological activity, for instance, can recycle carbon through the planet's mantle and atmosphere, stabilizing the climate over geological timescales. The quest to discover exoplanets, planets beyond our solar system, employs a fascinating array of methods, each unveiling new worlds in the vast expanse of space. This pursuit not only expands our understanding of planetary systems, but also brings us closer to answering the age-old question, are we alone in the universe? One of the most successful techniques for finding exoplanets is the transit method, which detects the slight dimming of a star's light as a planet passes in front of it. This method has been particularly fruitful, thanks to missions like NASA's Kepler Space Telescope, which monitored the brightness of thousands of stars, uncovering a diverse array of exoplanets. Another technique is the radial velocity method, which measures the star's motion towards and away from us, caused by the gravitational tug of an orbiting planet. This method can provide information about the planet's mass and its orbit. Direct imaging, though challenging, involves capturing actual images of exoplanets by blocking out the star's light, allowing astronomers to study the planet's atmosphere. Meanwhile, the gravitational microlensing method relies on the bending of light from a distant star caused by a planet's gravitational field, briefly magnifying the distant star's light in a way that can reveal an orbiting planet. Among the thousands of exoplanets discovered, several stand out for their unique characteristics or potential habitability. For instance, Kepler-22b was one of the first planets found in the habitable zone of its star, raising possibilities of liquid water on its surface. Another intriguing world is TRAPPIST-1e, one of 7 Earth-sized planets orbiting the dwarf star TRAPPIST-1, which has captured imaginations with its potential for water and habitability. Then there's Proxima Centauri b, located in the habitable zone of Proxima Centauri, the closest star to the Sun. Its discovery sparked excitement about the possibility of studying a potentially habitable planet that's relatively nearby in cosmic terms. Meanwhile, HD 209458b, known as Osiris, stands out for being the first planet where an atmosphere was detected, offering a glimpse into the composition of exoplanetary atmospheres. Each of these discoveries brings a unique insight into the diversity and complexity of planetary systems across the galaxy. They also underscore the remarkable progress in our ability to detect and study distant worlds, moving us closer to understanding the conditions that might support life elsewhere in the cosmos. The ongoing search for exoplanets not only pushes the boundaries of our knowledge, but also continually redefines our place in the universe, reminding us of the endless possibilities that lie among the stars. The existence of dark matter and the effects of dark energy on the universe's expansion are among the most profound discoveries in modern cosmology, reshaping our understanding of the universe's composition and its dynamic evolution. Dark matter, a form of matter that does not emit, absorb, or reflect light, making it invisible to current telescopic technology, has been inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the earliest pieces of evidence for dark matter came from the observation of the rotation curves of galaxies by Vera Rubin in the 1970s. Rubin found that stars at the outer edges of galaxies were moving faster than expected based on the visible mass alone, suggesting the presence of an unseen mass influencing their motion. Further evidence comes from the phenomenon of gravitational lensing, where the gravity of a massive object, like a galaxy cluster, bends the light of more distant galaxies behind it. The amount of bending observed indicates that there is much more mass present than what can be accounted for by visible matter alone, pointing to dark matter. Additionally, measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, provide a snapshot of the early universe that matches predictions only when dark matter is included, reinforcing its existence. On the other hand, dark energy, a mysterious force driving the accelerated expansion of the universe, has been primarily evidenced by observations of distant supernovae. In the late 1990s, astronomers studying Type Ia supernovae, which serve as standard candles for measuring cosmic distances, discovered that these supernovae were fainter than expected. This faintness implies that the universe's expansion has been accelerating, not slowing down due to gravity as previously thought. This acceleration can be explained by the presence of dark energy, which constitutes about 68% of the total energy content of the universe. The effects of dark energy are not only observed in the accelerated expansion of the universe, but also have profound implications for its ultimate fate. If dark energy continues to dominate, the universe may continue expanding indefinitely, leading to a cold and empty cosmos in the far future. Alternatively, if dark energy's nature changes, it could lead to different scenarios, including the recollapse of the universe or an even more rapid expansion. Together, dark matter and dark energy form the foundation of the Lambda cold dark matter model, the standard model of cosmology that describes the evolution of the universe from the Big Bang to its current state. Diving further into the unknown forces in space, we encounter phenomena such as quasars, pulsars, gamma-ray bursts, and the enigmatic nature of space magnetic fields. Each of these astronomical phenomena offers a unique window into the extreme environments and processes that govern the universe. Quasars, or quasi-stellar objects, are the intensely luminous hearts of distant galaxies, powered by supermassive black holes. As matter spirals into these black holes, it forms an accretion disk, heating up to incredible temperatures and emitting vast amounts of energy across the electromagnetic spectrum, especially as visible light, X-rays, and ultraviolet radiation. Quasars are among the most brilliant and distant objects in the universe, shining with the light of billions of stars, even though they are compact enough to fit within our solar system. They serve as crucial beacons in understanding the early universe, revealing how supermassive black holes grow and how galaxies form and evolve around them. Pulsars, on the other hand, are the remnants of massive stars that have exploded in supernovae and collapsed into dense neutron stars. These neutron stars are incredibly small, about 20 kilometers in diameter, but extraordinarily dense, with masses comparable to that of the Sun. Pulsars emit beams of electromagnetic radiation from their magnetic poles, and as they rotate, these beams sweep across space like the beams of a lighthouse. When the Earth intersects with one of these beams, we detect pulses of radiation, hence the name pulsar. Pulsars are precise cosmic clocks, allowing astronomers to study the properties of space and test theories of gravity. Gamma-ray bursts, or GRBs, are the most energetic explosions in the universe, briefly outshining entire galaxies with their extraordinary bursts of gamma rays. These bursts can last from a few milliseconds to several minutes and are thought to originate from two primary processes: the collapse of massive stars into black holes, leading to supernovae, or the collision of neutron stars. GRBs provide insights into the processes driving these cataclysmic events and the nature of the early universe, offering clues about the rate of star formation and the origins of heavy elements. Space magnetic fields, pervasive throughout the cosmos, play a fundamental role in shaping the interstellar medium, guiding cosmic rays, and influencing the formation and evolution of galaxies. These magnetic fields can be generated by the movement of conductive fluids inside stars and planets, a process known as the dynamo effect, or can be remnants from the early stages of the universe's formation. They are detected through their effects on cosmic particles and the polarization of light from distant stars and galaxies. Understanding space magnetic fields helps astronomers decipher the magnetic structures of galaxies, the behavior of interstellar gas and dust, and the dynamics of astrophysical jets. In the quest to understand life's potential beyond Earth, scientists have delineated essential conditions that must be met for life as we know it to thrive. These conditions include the presence of liquid water, a source of energy, and a suitable chemical environment that includes carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Liquid water acts as a solvent for biochemical reactions, energy is necessary for metabolic processes, and the right chemical elements are the building blocks of life. The search for signs of life, or biosignatures, on exoplanets and within our solar system employs a variety of innovative methods. For exoplanets, the transit method, which detects planets as they pass in front of their host stars, provides opportunities not only to discover new worlds, but also to analyze their atmospheres. During a transit, a small fraction of starlight filters through the planet's atmosphere, allowing scientists to identify the chemical signatures of gases that could indicate biological activity. For instance, the presence of oxygen, methane, or nitrous oxide in an exoplanet's atmosphere, especially in combinations unlikely to be produced abiotically, could suggest the possibility of life. Another method involves direct imaging, capturing light from the planets themselves, which allows for the study of their chemical composition, thermal structure, and even surface colors. Though challenging due to the faintness of planets compared to their stars, advances in technology are progressively making this more feasible. Within our solar system, missions to Mars, such as the rovers that traverse its surface, search for evidence of past or present microbial life by analyzing soil and rock samples. These rovers look for signs of organic compounds, water-related minerals, and isotopic signatures that could indicate biological processes. Europa and Enceladus, moons of Jupiter and Saturn respectively, with their subsurface oceans, are also prime candidates in the search for life. Future missions aim to probe these oceans, hidden beneath icy crusts for signs of life, using techniques ranging from flybys that sample water plumes ejected into space to landers or ice-penetrating probes. The search for life beyond Earth also extends to Venus, where the discovery of phosphine gas in its atmosphere has spurred interest, despite the planet's extreme surface conditions. While the presence of phosphine could have non-biological explanations, it underscores the diverse environments in which scientists are searching for life. Human space exploration, aimed at unlocking the mysteries of the cosmos and ensuring the long-term survival of our species, faces a host of challenges alongside its ambitious objectives. From the technical and physiological hurdles of long-duration travel to the logistical and ethical considerations of colonization efforts, these endeavors push the limits of current technology and human resilience. One of the primary challenges in long-duration space travel is ensuring the health and well-being of astronauts. Extended periods in space expose crews to significant risks, including the effects of microgravity on muscle and bone density, radiation exposure outside the Earth's protective magnetosphere, and the psychological stresses of confinement and isolation. Addressing these concerns requires innovative solutions, such as improved radiation shielding, exercise regimes to combat muscle and bone loss, and measures to support mental health. Another significant hurdle is the development of life support and sustainability systems that can operate efficiently over long periods. These systems must provide air, water, and food, recycling as much as possible to minimize resupply missions. Advances in closed-loop life support systems, which recycle waste products back into usable resources, are crucial for long-duration missions and the sustainability of space habitats. The technical challenges of propulsion and energy supply are also paramount. Current propulsion technologies limit the speed at which spacecraft can travel, extending mission durations and the time astronauts are exposed to space's hazards. Developing faster propulsion systems, such as nuclear thermal or electric propulsion, could significantly reduce travel time, making missions to Mars and beyond more feasible. Additionally, reliable energy sources are essential for powering spacecraft and future colonies. Solar power, nuclear reactors, and in situ resource utilization, extracting and using materials found on other planets, are among the solutions being explored. As human presence in space expands to include longer missions and eventual colonization, ethical and logistical considerations come to the forefront. Who will have the right to visit or settle in space? How will we ensure the protection of other planets' environments? The establishment of legal and ethical frameworks for space exploration and the use of space resources is critical. The objectives of human space exploration are as varied and ambitious as the challenges. They include conducting scientific research to understand the universe and our place in it, searching for extraterrestrial life, testing technologies for living and working in space, and eventually establishing human settlements on other planets to ensure humanity's survival. Mars, with its relatively Earth-like characteristics, has been a primary focus for colonization efforts, but the Moon is also seen as a stepping stone for deeper space exploration. Fast radio bursts, or FRBs, are one of the cosmos's most mysterious phenomena, brief flashes of intense radio waves from space that last only milliseconds yet emit as much energy as the Sun does in days or even weeks. First discovered in 2007, these enigmatic signals have puzzled astronomers and sparked a flurry of research aimed at deciphering their origins and implications. Originating billions of light-years away, FRBs are characterized by their incredible brightness and short duration. Despite their fleeting nature, they have been detected in various parts of the sky, with some sources emitting repeated bursts while others are observed as singular events. This distinction has led researchers to propose different mechanisms for their origins. Theories range from highly magnetized neutron stars, known as magnetars, and their explosive activities, to more exotic possibilities, such as connections to black holes, or even, though highly speculative and without evidence, signals from advanced extraterrestrial civilizations. The study of FRBs is not just about understanding these bursts themselves, but also about using them as cosmic tools. Due to their journey through the vast expanses of the universe, FRBs interact with the intergalactic medium, allowing scientists to probe the unseen matter distributed throughout the cosmos. This interaction with electrons and magnetic fields in space alters the properties of the bursts, providing clues about the distribution of matter in the universe, including the elusive dark matter. Moreover, the localization of FRBs to specific galaxies has opened new avenues for cosmological studies. By measuring the dispersion and delay of the signals caused by their interaction with cosmic matter, astronomers can estimate the universe's large-scale structure and even test theories of gravity and relativity over cosmic distances. The ongoing detection and study of FRBs, facilitated by advancements in telescope technology and global collaboration among observatories, promise to unravel more about these cosmic enigmas. Each new discovery brings us closer to understanding not only the nature of FRBs, but also the fundamental properties of the universe, from the distribution of matter to the extreme conditions around compact objects like neutron stars and black holes. Now, let's talk about rogue planets. Enigmatic wanderers of the cosmos, they are worlds that do not orbit a star but instead drift through space on their own. These mysterious objects challenge our traditional views of planetary systems and offer intriguing insights into the diversity and dynamism of the universe. The origins of rogue planets are as fascinating as they are varied. Some may have formed in orbit around a star before being ejected from their native systems by gravitational interactions, possibly with other planets, or as a result of a passing star's disruptive influence. Others might have formed independently in vast molecular clouds, much like stars, but failed to acquire enough mass to ignite nuclear fusion and shine as stars do. These processes underscore the chaotic nature of young planetary systems and the fragile balance that allows planets to remain in stable orbits. Rogue planets are intriguing not only because of their solitary journeys through the galaxy, but also because of the implications they hold for our understanding of planetary formation and the potential for life beyond Earth. The discovery of these wandering worlds suggests that planetary systems may be more dynamic and varied than previously thought. It also raises the possibility that rogue planets could outnumber stars in our galaxy, pointing to a vast population of unseen objects drifting in the darkness of space. The study of rogue planets poses significant challenges, as their lack of a bright star makes them difficult to detect. However, techniques such as gravitational microlensing, where a rogue planet passes in front of a distant star and briefly magnifies its light, have provided evidence of their existence. Future observations with more sensitive instruments may reveal more about these elusive worlds, including their sizes, compositions, and the conditions on their surfaces. One of the most captivating questions surrounding rogue planets is whether they could harbor life. While the absence of a host star would seem to preclude the possibility of a life-supporting environment, some theories suggest that a thick atmosphere or internal heat sources, such as residual heat from formation or radioactive decay, could provide the necessary conditions for life in some form. The exploration of these possibilities opens new avenues for the search for life in the universe, extending beyond the traditional focus on planets within the habitable zones of stars. Diving deeper into these unusual cosmic mysteries, the WOW signal represents one of the most intriguing and enduring mysteries in the search for extraterrestrial intelligence. Detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University, the WOW signal was a sudden, strong radio signal lasting 72 seconds, originating from the direction of the constellation Sagittarius. The signal's intensity and characteristics were so remarkable that upon reviewing the data, astronomer Jerry R. Amon circled the alphanumeric sequence representing the signal's intensity, 6 EKWJ5, and wrote WOW in the margin, giving the signal its name. The origins of the WOW signal have been the subject of speculation and investigation for decades. Its narrowband frequency, closely matching the hydrogen line, 1420 MHz, is what one might expect from an intentional broadcast because hydrogen is the most abundant element in the universe, making this frequency a logical choice for interstellar communication. However, despite numerous attempts, the signal has never been detected again, leading to a wide range of theories about its source, including interstellar scintillation, a passing comet, or a burst of natural background noise. Yet, none of these explanations have definitively solved the mystery, leaving the possibility open that the signal could have been a transmission from an extraterrestrial civilization. The implications of the WOW signal extend far beyond its potential origins. It has significantly impacted the search for extraterrestrial intelligence, SETI, highlighting both the potential and the challenges of detecting and interpreting signals from beyond our planet. The WOW signal has underscored the importance of continuous monitoring of the cosmos for signs of intelligent life and has driven the development of more sensitive detection methods and protocols for verifying extraterrestrial signals. The WOW signal has captivated public imagination, serving as a poignant reminder of our place in the universe and the possibility that we are not alone. The fate of the universe, a subject of both fascination and intense study, is intertwined with cutting-edge theoretical frameworks like string theory, the concept of the multiverse, and the speculative possibilities of wormholes and time travel. These ideas not only expand our understanding of the cosmos, but also open up profound questions about the nature of reality and our place within it. One potential outcome for the universe's fate, based on current understanding, is the continued acceleration of its expansion, leading to a scenario known as the Big Freeze, or heat death. In this scenario, the universe would expand indefinitely, stars would burn out, and galaxies would drift apart, eventually leading to a cold, dark, and lifeless cosmos. This outcome is supported by observations of dark energy, a mysterious force that appears to be driving the acceleration of the universe's expansion. Another possibility is the Big Crunch, where the universe's expansion eventually reverses, leading all matter and energy to collapse back into a singularity, potentially setting the stage for another Big Bang. However, current observations suggest that the universe's expansion is accelerating, making the Big Crunch less likely. Theoretical frameworks like string theory, which proposes that the fundamental constituents of the universe are one-dimensional strings rather than point-like particles, offer a deeper understanding of the universe's fabric. String theory is also a cornerstone of the multiverse concept, which posits that our universe might be just one of many universes, each with its own physical laws and constants. This idea challenges the notion of our universe's uniqueness and raises the possibility that other universes could harbor vastly different forms of existence. Wormholes, hypothetical passages through space-time that could connect distant points in the universe or different universes altogether, offer intriguing possibilities for space travel and communication. While purely speculative at present and fraught with theoretical challenges, wormholes capture the imagination as potential shortcuts through the cosmos, opening up discussions about the nature of space-time and the possibility of interstellar or even interuniversal travel. Time travel, another speculative concept, is deeply entwined with our understanding of the universe's structure. While time travel to the future is theoretically possible through the effects of time dilation as predicted by Einstein's theory of relativity, travel to the past presents formidable paradoxes and challenges under current physical laws. However, the exploration of these concepts pushes the boundaries of our understanding of causality and the fabric of space-time. In exploring these potential outcomes and theoretical frameworks, we confront the limits of our current knowledge and the vastness of the unknown. The fate of the universe, the reality of the multiverse, and the possibilities of wormholes and time travel not only challenge our understanding of the cosmos, but also invite us to ponder the fundamental nature of existence. As we delve deeper into these mysteries, we continue to push the frontiers of science, philosophy, and our quest to understand the cosmos. The likelihood of extraterrestrial life and intelligence has long captivated scientists and the public alike, leading to the development of several frameworks and efforts aimed at understanding and finding life beyond Earth. Central to this quest is the Drake equation, a probabilistic formula proposed by astronomer Frank Drake in 1961 to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The Drake equation synthesizes several variables into a single formula, each representing a factor considered necessary for the development of such civilizations. These factors include the rate of star formation in our galaxy, the fraction of those stars that have planetary systems, the number of planets per solar system with an environment suitable for life, the fraction of suitable planets on which life actually appears, the fraction of life-bearing planets on which intelligent life evolves, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and the length of time such civilizations release detectable signals into space. While the equation provides a framework for estimating the number of extraterrestrial civilizations, the actual values of most of its variables remain uncertain. This uncertainty stems from our limited knowledge of the processes that lead to the emergence of life and the development of technological civilizations, as well as the vastness and complexity of the Milky Way galaxy. Consequently, estimates of the number of communicative civilizations in the galaxy have varied widely, depending on the values assigned to the variables in the equation. Despite its uncertainties, the Drake equation has played a crucial role in framing the scientific discussion about extraterrestrial life and guiding research and exploration efforts. It highlights the key factors that influence the emergence of life and civilization beyond Earth and serves as a starting point for debates and studies in astrobiology and the search for extraterrestrial intelligence. The efforts of SETI, an initiative dedicated to searching for signs of intelligent life beyond Earth, have been directly influenced by the Drake equation. SETI researchers use a variety of techniques, including listening for radio and optical signals that might be emitted by extraterrestrial technologies. Although no definitive evidence of extraterrestrial intelligence has been found to date, SETI's ongoing efforts underscore the scientific community's commitment to exploring the possibility of life beyond our planet. Following the exploration of the Drake equation, we encounter the Fermi paradox, which starkly contrasts the equation's optimistic numbers with the conspicuous silence of the cosmos. Named after physicist Enrico Fermi, the paradox articulates a compelling contradiction. Given the high probability of extraterrestrial civilizations' existence, why have we found no evidence of them? The universe is vast, with billions of stars in our galaxy alone, many of which host planets in habitable zones where life as we know it could thrive. The age of the universe allows ample time for intelligent life to arise and make its presence known across the cosmic expanse. Yet, our searches for signals or signs of such civilizations have yielded nothing but silence. This silent void raises profound questions about the nature of life in the universe and our understanding of it. Several hypotheses have been proposed to explain the Fermi paradox. One suggestion is that while life may be common, the emergence of intelligent life capable of interstellar communication is exceedingly rare. Another possibility is the Great Filter hypothesis, which posits that there is a highly improbable step required for life to progress from simple to complex and intelligent forms, and humanity has either passed this filter or it lies ahead, posing a dire risk to our survival. Other explanations delve into the behavior and fate of civilizations, suggesting that technological civilizations may have short lifespans, either self-destructing or shifting their communications to modes undetectable to us. Additionally, there's the concept of the zoo hypothesis, which speculates that extraterrestrial civilizations intentionally avoid contact with humanity to allow for natural evolution and societal development, much like zookeepers trying to avoid disturbing the animals. Diving into the realm of cosmic anomalies brings us to the Great Attractor, a mysterious region in space that exhibits a gravitational force strong enough to affect the motion of galaxies over hundreds of millions of light years. Located in the direction of the Hydra and Centaurus constellations, the Great Attractor lies at a distance of approximately 220 million light years from Earth. This region poses a significant puzzle to astronomers, because it influences the velocities of galaxies, including our own Milky Way, drawing them towards it at an astonishing rate of millions of kilometers per hour. The complexity of studying the Great Attractor stems from its position in the zone of avoidance, an area of the sky obscured by the dust and gas of the Milky Way's galactic plane, making direct observation challenging. Despite these difficulties, advances in X-ray and radio astronomy have allowed scientists to peer through the galactic dust and begin to unravel the mystery. The evidence suggests that the Great Attractor is not a single massive entity, but rather a concentration of galaxy clusters, forming a part of an even larger structure known as the Laniakea supercluster, which encompasses our galaxy and about 100,000 others. The gravitational pull of the Great Attractor and its role in the motion of galaxies highlight the interconnectedness of cosmic structures and the dynamic nature of the universe. It serves as a reminder of the vast scales and forces at play beyond our local environment, pushing the boundaries of our understanding of the cosmos. Diving into the mysteries of our solar system, unusual comet orbits stand out as celestial puzzles that intrigue scientists and astronomers. Comets, often described as dirty snowballs, are composed of ice, rock, and organic compounds, and their orbits can tell us a great deal about the outer reaches of our solar system and the forces at play within it. Some comets exhibit highly eccentric orbits, bringing them close to the Sun, where they develop spectacular tails, before sending them back into the distant reaches of the solar system, or even ejecting them from the solar system entirely. These orbits challenge our understanding of the solar system's dynamics and hint at the influence of unseen objects or events. One explanation for these unusual orbits is the gravitational influence of the Oort cloud and the Kuiper belt, two vast regions of space filled with icy bodies located beyond the orbit of Neptune. The Oort cloud in particular is thought to be a spherical shell surrounding the solar system, home to billions of comets. Occasionally, the gravitational pull from passing stars or the galactic tide, the gravitational force exerted by the Milky Way itself, can disturb comets in these regions, sending them into the inner solar system on highly eccentric orbits. Another fascinating theory involves the presence of an as-yet undiscovered massive object in the outer solar system, sometimes referred to as Planet 9. This hypothetical planet could be responsible for the unusual orbits observed in some trans-Neptunian objects and comets, shepherding them into orbits that confound expectations based on the known gravitational influences of the solar system. The study of comet orbits not only deepens our understanding of the solar system's structure and the forces shaping it, but also provides insights into the solar system's history. By tracing the paths of these icy wanderers, scientists can glean information about the distribution of mass in the solar system's outer regions and the potential for interactions with interstellar objects. As our observational techniques and computational models improve, so too will our understanding of these unusual comet orbits, offering answers to long-standing questions and undoubtedly raising new ones about the complex dance of celestial bodies within our solar system. Titan and Enceladus, two of Saturn's moons, are captivating celestial bodies that have intrigued scientists with their unique and complex phenomena, significantly advancing our understanding of the diversity and potential habitability of environments within our solar system. Titan, Saturn's largest moon and the second largest in the solar system, is enveloped by a thick, nitrogen-rich atmosphere that is laced with organic molecules, some of which are the building blocks of life as we know it. This dense atmosphere creates a veiled world beneath, with a surface showcasing rivers, lakes, and seas, not of water, but of methane and ethane. These hydrocarbon seas are of particular interest because they represent an environment entirely alien to Earth, yet possibly capable of supporting life forms adapted to cold, liquid methane environments. Additionally, Titan's atmosphere undergoes a cycle similar to Earth's water cycle, but with methane and ethane, including clouds, rain, and liquid bodies on the surface, offering a fascinating parallel to Earth's hydrological dynamics in an utterly alien context. Enceladus, on the other hand, is a smaller moon of Saturn, famous for its active geysers ejecting plumes of water vapor and ice particles from cracks in its icy surface. These geysers hint at a subsurface ocean beneath the moon's icy crust, raising the tantalizing possibility of an environment where life could exist. The ejected material, which contributes to one of Saturn's rings, has been directly sampled by spacecraft, revealing complex organic compounds, salts, and silica particles. The presence of these compounds suggests that Enceladus's ocean is not only liquid, but also in contact with the Moon's rocky mantle, where hydrothermal processes could provide the energy necessary for life. The phenomena observed on Titan and Enceladus underscore the diversity of potentially habitable environments in our solar system beyond the Earth. Titan challenges our concepts of habitability with its cold, hydrocarbon-based system, while Enceladus presents a more familiar water-based potential habitat, albeit under the ice. Both moons exemplify the varied ways in which the conditions for life might exist and persist in the cosmos, expanding the search for extraterrestrial life to include worlds with environments radically different from our own. As missions continue to explore these moons and others like them, we inch closer to understanding the complexity of the solar system's moons, the processes that drive their unique phenomena, and the potential for life in environments once thought to be inhospitable. The nature of spacetime, a foundational concept in modern physics, intertwines the three dimensions of space with the one dimension of time into a single four-dimensional continuum. This revolutionary idea, rooted in Albert Einstein's theory of general relativity, posits that the presence of mass and energy warps the fabric of spacetime, dictating the motion of objects and the flow of time itself. Spacetime is not a static backdrop against which events unfold, but an active, dynamic entity that is shaped by and shapes the universe's contents. The Sun, Earth, and all celestial bodies, through their mass, create curvatures in spacetime that dictate their gravitational interactions. This curvature is what we perceive as gravity. For instance, Earth orbits the Sun not because it is being pulled by the Sun in a direct manner, but because the Sun's massive presence has curved spacetime in such a way that Earth's path through space is a stable orbit. The implications of spacetime being a malleable fabric extend to how we understand the movement of light, the flow of time, and the structure of the universe. Light, although it has no mass, follows the curvature of spacetime, leading to phenomena such as gravitational lensing, where light from a distant star is bent around a massive object like a galaxy cluster. Similarly, the flow of time is affected by the warping of spacetime. Time moves slower in stronger gravitational fields, a prediction of general relativity confirmed by precise experiments. This effect, known as gravitational time dilation, has practical applications, such as adjustments made to account for time differences between GPS satellites in orbit and receivers on Earth. The concept of spacetime has not only deepened our understanding of gravity, but also laid the groundwork for exploring more complex phenomena, such as black holes and the expansion of the universe. Black holes, regions of spacetime with gravity so strong that nothing, not even light, can escape, represent extreme distortions of spacetime where the known laws of physics reach their limits. The universe's expansion, on the other hand, suggests that spacetime itself is stretching, carrying galaxies with it and leading to the observed redshift of distant galaxies. The concept of the universe as finite yet unbounded is one of the most intriguing aspects of modern cosmology, offering a way to reconcile the vastness of the cosmos with the possibility of its having a limited volume. This idea, rooted in the geometry of spacetime described by general relativity, suggests that the universe can be spatially finite without having any edges or boundaries. To understand this concept, one can draw an analogy with the surface of the Earth. Imagine the Earth's surface as a two-dimensional space. It is finite in area, meaning you can only travel so far before returning to your starting point, yet it has no edges where you could fall off. Extending this analogy to the three-dimensional space of the universe, it's possible for the universe to curve back onto itself in a higher dimension, creating a closed geometry. In such a universe, if you could travel far enough in a straight line, you would eventually return to your starting point, despite never encountering a boundary or edge. This concept arises from Einstein's theory of general relativity, which allows for various possible shapes of the universe depending on its density and the nature of its expansion. A closed universe, one that is finite yet unbounded, would result from a density high enough to eventually halt the expansion of the universe and reverse it into a contraction, leading to a big crunch. However, current observations, including measurements of the cosmic microwave background radiation and the rate of the universe's expansion, suggest that the universe is flat on large scales and likely infinite in extent. Yet, the possibility of a finite yet unbounded universe remains a fascinating topic of theoretical exploration. The potential for higher dimensions beyond the 3 spatial dimensions and 1 time dimension we experience in our daily lives opens up a realm of fascinating possibilities that stretch the boundaries of our understanding of the universe. This concept, which is integral to several advanced theories in physics, including string theory and M-theory, suggests that the universe contains more dimensions than are apparent to us. In string theory, for instance, particles are not point-like entities but rather one-dimensional strings that vibrate at different frequencies. These vibrations determine the particle's properties, such as mass and charge. To be consistent and free of anomalies, string theory requires the existence of additional spatial dimensions, specifically 10 dimensions, 9 spatial dimensions plus 1 time dimension. These extra dimensions are hypothesized to be compactified or curled up at scales so small that they are undetectable by current instruments. The existence of higher dimensions could provide explanations for several phenomena in physics that are otherwise difficult to account for, such as the relative weakness of gravity compared to the other fundamental forces. If gravity can leak into extra dimensions, this could explain why it appears weaker in the 4-dimensional space-time we inhabit. Moreover, higher dimensions offer intriguing possibilities for the universe's structure and the fundamental nature of reality. They could allow for parallel universes or multiple branes, multidimensional objects, floating in a higher dimensional space, with our observable universe residing on one of these branes. Interactions between branes in the higher dimensional space could potentially give rise to phenomena within our 4-dimensional universe, such as the Big Bang. The exploration of higher dimensions also has implications for unifying the forces of nature. The quest for a theory of everything, a single, coherent theoretical framework that fully explains and links together all physical aspects of the universe, relies on the concept of higher dimensions to unify general relativity, which governs the macroscopic world, with quantum mechanics, which governs the subatomic world. The Sun, a colossal sphere of hot plasma at the center of our solar system, maintains its energy output through a process known as nuclear fusion. At its core, the Sun fuses hydrogen atoms into helium under extreme pressures and temperatures, a reaction that releases immense amounts of energy. This process is not only the source of the Sun's light and heat, but also the engine driving its long-lasting luminosity. In the Sun's core, where temperatures soar above 15 million degrees Celsius, 27 million degrees Fahrenheit, hydrogen atoms are squeezed under such tremendous pressure that they overcome their natural repulsion for one another. This environment facilitates the fusion of hydrogen nuclei, protons, to form helium-4 nuclei in a series of steps known as the proton-proton chain reaction. Each of these fusion reactions converts a tiny amount of mass into energy, according to Einstein's famous equation E equals mc², where E is energy, m is mass, and c is the speed of light. This energy is initially released as gamma rays, which then make their way to the Sun's surface, or photosphere, taking thousands of years. By the time this energy reaches the surface and is emitted as sunlight, it has mostly been transformed into visible light and other electromagnetic radiation. This fusion process is incredibly efficient, converting millions of tons of hydrogen into helium each second, yet it is also slow enough that the Sun has been shining for about 4.6 billion years and will continue to do so for approximately 5 billion more. The Sun's stability and consistent energy output are crucial for life on Earth, providing the warmth and light necessary for life processes. Solar phenomena, ranging from the benign to the potentially disruptive, have profound effects on Earth, influencing everything from our planet's climate to the technology we rely on daily. These phenomena include solar flares, coronal mass ejections, CMEs, solar wind, and the solar cycle, each impacting Earth in unique ways. Solar flares are intense bursts of radiation emanating from the release of magnetic energy associated with sunspots. While the light from a solar flare can reach Earth in just 8 minutes, the high-energy particles can take hours to days to arrive. Solar flares can affect radio communications, GPS signals, and power grids by ionizing the Earth's upper atmosphere, the ionosphere, disrupting the propagation of radio waves. Coronal mass ejections, or CMEs, are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. CMEs can eject billions of tons of coronal material and carry an embedded magnetic field, frozen in flux, that is stronger than the background solar wind interplanetary magnetic field strength. When these ejections collide with the Earth's magnetosphere, they can cause geomagnetic storms, potentially disrupting satellite operations, power grids, and navigation systems. The interaction of CMEs with the Earth's magnetosphere can also lead to spectacular auroras near the polar regions. Solar wind, a stream of charged particles released from the upper atmosphere of the Sun, the corona, affects Earth's magnetosphere and can lead to geomagnetic storms. Continuous but varying in intensity, the solar wind interacts with Earth's magnetic field, compressing it on the day side and extending the night side magnetic tail. This interaction can energize particles trapped in the Earth's magnetosphere, causing them to precipitate into the Earth's upper atmosphere and produce auroras. The solar cycle, an approximately 11-year cycle that marks the rhythmic increase and decrease in solar activity, including the frequency of sunspots, solar flares, and CMEs, influences Earth's climate and space weather conditions. During periods of maximum solar activity, or solar maxima, the Sun emits more ultraviolet radiation, which can lead to greater ozone production in Earth's stratosphere, affecting atmospheric circulation patterns and potentially influencing weather and climate on a regional scale. Beyond these direct impacts, solar phenomena can have broader implications for Earth. For instance, prolonged periods of low solar activity, such as the Maunder minimum in the 17th century, have been associated with cooler global temperatures, suggesting a link between solar activity and climate. Moreover, the increasing reliance on technology makes our society more vulnerable to the effects of solar storms on communication and navigation systems, highlighting the importance of monitoring solar activity and developing resilience strategies. Speculating on the characteristics of advanced civilizations beyond our own involves a fascinating blend of scientific knowledge, philosophical inquiry, and imaginative thinking. Such civilizations, if they exist, would likely have mastered technologies and societal structures far beyond our current capabilities. Their characteristics can be explored through various frameworks, including the Kardashev scale, which categorizes civilizations based on their energy consumption and technological capabilities. A Type 1 civilization on the Kardashev scale has harnessed the energy resources of its entire planet. This would include the full utilization of solar energy, geothermal energy, and other planetary resources. Such a civilization would have overcome many of the environmental and societal challenges we face, such as climate change and energy scarcity. They might have advanced forms of sustainable living with technologies that efficiently recycle waste, manage ecosystems, and possibly control weather patterns to optimize agricultural productivity and prevent natural disasters. A Type 2 civilization extends its energy harnessing capabilities to its entire star system. This includes, most famously, the concept of a Dyson sphere, or similar megastructures that could capture a significant portion or all of the energy output of their star. With such energy at their disposal, these civilizations would likely have mastered space travel within their system, possibly colonizing and terraforming other planets and moons. They could have technologies that manipulate the orbits of planetary bodies, redirect asteroids for mining or defense, and harness the power of other phenomena like black holes or neutron stars. A Type 3 civilization, the pinnacle of the Kardashev scale, controls energy on the scale of its entire galaxy. The capabilities of such a civilization are difficult to fathom. They might be capable of interstellar travel, creating and destroying stars, manipulating the fabric of space-time, and possibly even accessing and exploiting the energy of parallel universes if such concepts are physically meaningful. Their understanding of physics and the universe would be so advanced that their technologies would seem almost magical to us. Across these speculative stages, several characteristics of advanced civilizations can be inferred. Advanced civilizations would possess technology that integrates seamlessly with the laws of physics, possibly blurring the lines between technology and nature. Their technologies would likely be sustainable, highly efficient, and capable of manipulating matter and energy at fundamental levels. The survival of a civilization to reach higher levels of the Kardashev scale implies a degree of social and ethical maturity. They would need to have overcome self-destructive tendencies, such as warfare and exploitation, achieving a harmonious balance between technological advancement and peace. Advanced civilizations would likely retain a drive for exploration and knowledge, pushing the boundaries of science, philosophy, and possibly even transcending physical existence in ways we cannot imagine. The methods and motives for communication with other civilizations, if they choose to do so, would reflect their advanced understanding and capabilities. They might engage in the seeding of life, mentoring younger civilizations, or ensuring the stability of the cosmos against existential threats. A deeper understanding of the universe has profound implications for our perception of our place within the cosmic tapestry. As our knowledge expands through advancements in astronomy, physics, and cosmology, we are continually reminded of the vastness of the universe and the intricate complexities that govern its workings. This expanding understanding influences our perception in several significant ways, reshaping our worldview and challenging our assumptions about life, existence, and our significance in the cosmos. One of the most striking realizations that come from delving deeper into the universe's mysteries is the recognition of our sheer smallness. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and potentially countless planets. This realization can evoke a sense of humility, highlighting the fragility and preciousness of life on our tiny planet in the vast expanse of space. It underscores the rarity and value of our existence, fostering a sense of universal stewardship and a desire to preserve and cherish the delicate balance of life on Earth. Simultaneously, our deepening understanding of the universe can also inspire a sense of connection and unity. The laws of physics that govern the movement of galaxies also influence the smallest particles on Earth. The same elements that make up the stars are found within us. This universal commonality suggests a profound interconnectedness of all things, from the smallest to the grandest scales, reinforcing the idea that we are an integral part of the cosmos, not mere observers or accidents. The exploration of the universe and the search for extraterrestrial life expand our notions of habitability and life's potential diversity. Discoveries of exoplanets in habitable zones around other stars, and studies of extreme environments on Earth where life thrives, suggest that life could be more common and varied than previously imagined. This possibility challenges anthropocentric views and invites us to consider a broader spectrum of life forms and intelligences, potentially reshaping our understanding of life's nature and the possibilities for communication and interaction with non-human intelligences. The interactions between dark matter and baryonic matter, the normal matter that makes up stars, planets, and all visible objects, play a crucial role in shaping the structure and dynamics of galaxies, influencing both their shape and rotation curves in significant ways. Dark matter, though invisible and not directly detectable, constitutes about 85% of the universe's total matter content. Its presence is inferred from its gravitational effects on visible matter, light, and the structure of the universe. One of the key insights into dark matter comes from observing galaxy rotation curves, the way the velocity of stars and gas clouds orbiting the galaxy center changes with distance from the center. According to Newtonian mechanics, one would expect the rotational speed of objects orbiting a galaxy's center to decrease with distance from the center, similar to how planets in the solar system orbit the sun. However, observations show that the rotational speeds of stars in galaxies remain constant or even increase slightly with distance from the galactic center, defying these expectations. This discrepancy suggests the presence of a substantial amount of unseen mass, attributed to dark matter, exerting gravitational influence. Dark matter forms vast halos that envelop galaxies, extending far beyond the visible edge of the galaxy. The gravitational pull of this dark matter halo is what keeps stars moving at higher velocities than would be expected based solely on the visible mass. This not only explains the flat rotation curves of galaxies, but also plays a critical role in their formation and evolution. During the early stages of the universe, dark matter clumps formed the gravitational scaffolding around which baryonic matter coalesced to form stars, galaxies, and larger structures. The distribution and density of dark matter in these halos influenced the shape and type of galaxies that formed. For instance, dense, compact halos might lead to the formation of elliptical galaxies, while more extended halos with specific angular momentum distributions can give rise to spiral galaxies. The interactions between dark matter and baryonic matter are essential for understanding the large-scale structure of the universe. Dark matter's gravitational effects enhance the clumping of matter in certain regions, leading to the web-like structure of the cosmos, with galaxies and clusters of galaxies linked by filaments of dark matter and separated by vast voids. Discoveries about the intergalactic medium, or IGM, have significantly reshaped our understanding of galaxy formation, highlighting the dynamic and interconnected nature of the universe. The IGM, which consists of diffuse gas and plasma that fills the vast spaces between galaxies, plays a critical role in the cosmic web's structure and evolution, acting as both a reservoir for galaxy formation and a record of the processes that shape the universe. One key discovery is the detection of the cosmic web, a vast network of filamentary structures composed of dark matter and gas that stretches across the universe, linking galaxies and galaxy clusters. Observations, particularly through the absorption lines in the spectra of distant quasars, bright, active galaxies far away, have revealed the presence of hydrogen and other elements in the IGM. These absorption lines, known as the Lyman alpha forest, have provided valuable insights into the distribution, temperature, and composition of the IGM, confirming the existence of the cosmic web and its role in galaxy formation. The realization that the IGM is not only a repository of matter, but also a dynamic participant in galaxy evolution has been transformative. Gas from the IGM falls into the gravitational wells created by dark matter, cooling and condensing to form stars and galaxies. This process, known as accretion, is fundamental to galaxy formation and growth. Furthermore, feedback mechanisms from star formation and active galactic nuclei, where energy is injected back into the IGM, regulate the flow of gas into and out of galaxies, influencing their ability to form stars. Another groundbreaking discovery has been the detection of the missing baryons. Early observations of galaxies and galaxy clusters accounted for only a fraction of the ordinary matter predicted by the Big Bang theory. Studies of the IGM have uncovered these missing baryons in the form of warm-hot intergalactic medium, or WIM, a tenuous, partially ionized gas that permeates the filaments of the cosmic web. The WIM had been difficult to detect due to its diffuse nature and the high temperatures at which it emits and absorbs radiation. But recent observations using X-ray and ultraviolet telescopes have begun to reveal its properties and distribution. The mass of a star is the principal determinant of its life cycle, dictating not only how the star lives, but also how it dies. This mass influences the star's core pressure and temperature, determining the nuclear fusion reactions that can occur, and thus the star's luminosity, temperature, and lifespan. Depending on its initial mass, a star may end its life as a white dwarf, neutron star, or black hole, each marking a different evolutionary path in the cosmos. Stars with masses up to about 8 times that of the Sun follow a similar evolutionary path. They spend the majority of their lives fusing hydrogen into helium in their cores, a phase known as the main sequence. Once the hydrogen fuel is exhausted, these stars expand into red giants, where the core contracts and heats up, enabling the fusion of helium into carbon and oxygen in a shell around the core. For stars like the Sun, This is where nuclear fusion essentially ends. When the nuclear fuel is depleted, the outer layers of the star are ejected, creating a planetary nebula, while the core remains as a white dwarf, a hot, dense remnant roughly the size of Earth, but with a mass close to the Sun's. White dwarfs gradually cool and fade over billions of years. Stars with masses significantly greater than the Sun undergo more complex and energetic lives. After exhausting their hydrogen, these stars become supergiants and can fuse heavier elements in their cores, sequentially burning through helium, carbon, oxygen, and so on, up to iron. Iron fusion, however, consumes energy rather than releases it, leading to a rapid core collapse once a significant amount of iron has accumulated. This collapse triggers a supernova explosion, one of the universe's most spectacular events. The star's outer layers are blown away, while the core collapses into an extremely dense object. If the core's mass is about 1.4 to 3 times that of the Sun, the Chandrasekhar limit, it becomes a neutron star, an object so dense that protons and electrons combine to form neutrons. A sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. For cores with masses exceeding roughly 3 solar masses, the gravitational collapse results in a black hole, a point in space where gravity is so strong that not even light can escape. The Schwarzschild radius, or event horizon, marks the boundary beyond which nothing can return. The mass of a star, therefore, sets the stage for its entire life and ultimate fate, from tranquil existences marked by gentle winds of ejected material to violent ends that outshine galaxies. These end states, white dwarfs, neutron stars, and black holes, contribute to the cosmic cycle of matter, seeding the universe with the heavy elements forged in their crucibles, elements that will become part of future stars, planets, and possibly life forms, continuing the grand cycle of cosmic evolution. The study of binary star systems, pairs of stars orbiting a common center of mass, plays a crucial role in enhancing our understanding of stellar evolution and the synthesis of heavy elements. These systems, which make up a significant portion of the stars in the universe, offer unique insights into the lives and deaths of stars, especially in scenarios where one star can significantly influence the evolution of its companion. Binary star systems provide natural laboratories for studying stellar evolution under the influence of a companion. Observing how stars in binary systems interact allows astronomers to test and refine models of stellar structure, evolution, and nucleosynthesis, the process by which stars create heavier elements from lighter ones. One critical phase observed in some binary systems is mass transfer. If one star expands into a red giant or supergiant phase, material from its outer layers can spill over onto its companion, altering the recipient star's mass, composition, and evolutionary path. This process can lead to a variety of exotic objects and phenomena, including blue stragglers, stars that appear younger than they are, cataclysmic variables, and symbiotic stars. Through mass transfer, binary systems can bypass certain evolutionary stages or accelerate into later stages, providing insights into the flexibility and diversity of stellar evolution. Binary star systems, particularly those involving compact objects like white dwarfs, neutron stars, or black holes, are key sites for the synthesis of heavy elements. The most famous example is the merger of 2 neutron stars, which was observed in 2017 through both gravitational waves and electromagnetic radiation. This landmark event confirmed that neutron star mergers are a primary site for the rapid neutron capture process, our process, a nucleosynthesis pathway responsible for creating approximately half of the elements heavier than iron, including gold and platinum. Similarly, systems where a white dwarf accretes material from a companion until it reaches a critical mass can undergo a thermonuclear explosion known as a Type Ia supernova. These supernovae play a vital role in enriching the interstellar medium with iron peak elements and provide a standard candle for measuring cosmic distances. Interactions in binary systems can lead to scenarios where elements synthesized in one star are exposed to the surface of another, offering observable clues about internal processes like dredge-ups and nucleosynthesis that occur in stars. Binary systems are also crucial for understanding the end stages of stellar evolution. For instance, the observation of binary systems containing black holes or neutron stars can shed light on the life cycles of massive stars and the conditions needed to form these dense remnants. The gravitational wave detections from merging black holes and neutron stars in binary systems have opened a new era of astronomy, providing insights into the properties of matter at extreme densities, the rates of such mergers, and their role in the universe's evolution. The exploration of exoplanet atmospheres, though still in its infancy, has already begun to reveal the astonishing diversity of environments that exist beyond our solar system. By comparing these atmospheres to those of planets within our solar system, scientists are uncovering clues about the formation, composition, and potential habitability of these distant worlds. This comparison is crucial for understanding the vast range of planetary environments and assessing the potential for life elsewhere in the universe. Exoplanet atmospheres exhibit a wide range of compositions, temperatures, and weather patterns, some of which are similar to the planets in our solar system, while others are entirely alien. For instance, hot Jupiters, gas giants that orbit very close to their stars, have been found with atmospheres dominated by hydrogen and helium, similar to Jupiter and Saturn, but at temperatures so high that they can vaporize metals. Observations have detected iron, titanium, and even water vapor in the atmospheres of some of these exoplanets, under conditions vastly different from those found in the solar system. Smaller rocky exoplanets have also been observed, with some showing evidence of atmospheres that could potentially harbor water vapor, a key ingredient for life as we know it. However, the range of atmospheric compositions is broad, with some exoplanets exhibiting atmospheres rich in carbon dioxide or methane, and others with no atmosphere at all, reminiscent of Mercury or the Moon. The diversity of exoplanet atmospheres provides insights into the processes of planet formation and evolution. For example, the presence of heavy elements and compounds in the atmospheres of hot Jupiters suggests a complex history of accretion and possibly indicates interactions with the protoplanetary disk or other bodies in their systems. Similarly, the variety in the atmospheric composition of rocky exoplanets points to differences in their initial material, distance from their star, and geological activity. When assessing the potential for life, the comparison of exoplanet atmospheres to those in our solar system highlights the importance of an atmosphere's composition and stability. An atmosphere that can retain liquid water on the planet's surface, protect life from harmful radiation, and maintain a stable climate over geological timescales is ideal. In our solar system, Earth is the only planet that meets all these criteria, serving as a model for identifying potentially habitable exoplanets. The detection of biosignature gases such as oxygen, ozone, methane, or nitrous oxide in an exoplanet's atmosphere could suggest biological activity, especially if these gases are found in combinations that are unlikely to be produced through abiotic processes alone. However, the interpretation of these signatures is complex, as they can also be produced by non-biological means under certain conditions. Recent findings in the field of planetary science have significantly challenged and expanded our understanding of planet formation and the diversity of planetary systems. These discoveries, made possible by advanced telescopes and space missions, have unveiled a cosmos filled with an astonishing variety of planets and planetary systems, pushing the boundaries of existing theoretical models. One of the most striking revelations has been the discovery of hot Jupiters, gas giants that orbit very close to their host stars, in environments much hotter than those in which gas giants form within our solar system. Their existence challenges traditional models of planet formation, which suggest that gas giants should form in the colder outer regions of a planetary system before possibly migrating inward. The mechanisms of this migration and the conditions under which these planets form and survive in such close proximity to their stars are active areas of research, prompting scientists to rethink theories of planetary system evolution. Another surprising discovery has been that of super-Earths and mini-Neptunes, types of planets with no direct analog in our solar system. These planets, which range in mass between Earth and Neptune, raise questions about the processes that determine planet composition and the transition between rocky planets and gas giants. The diversity in size, density, and composition of these planets suggests a complexity in planet formation processes that was not anticipated in earlier models, which primarily focused on the solar system's architecture. The finding of planetary systems around binary and even trinary star systems further challenges our understanding. While the formation of stable planetary orbits in such dynamic environments was once thought to be improbable, numerous planets have been discovered in these complex settings. This has implications for the dynamics of planet formation and survival, indicating that planetary systems can be more resilient and versatile than previously believed. Additionally, the detection of free-floating planets, those not bound to any star and wandering through the galaxy, suggests that planet ejection from developing or mature planetary systems might be more common than anticipated. This challenges our understanding of the stability and longevity of planetary systems and raises questions about the mechanisms driving these ejections. These findings, among others, are reshaping our understanding of the diversity of planetary systems and the processes of planet formation. They highlight the unique characteristics of our solar system and its formation, while unveiling the broad range of environments in which planets can form and evolve. As a result, astronomers and planetary scientists are continually refining their theories, incorporating new observations, and developing more sophisticated models to account for the diversity and complexity of planetary systems throughout the galaxy. Dark energy, a mysterious force that is accelerating the expansion of the universe, constitutes about 68% of the universe's total energy. Its discovery in the late 1990s through observations of distant supernovae has profoundly shifted our understanding of the cosmos, presenting new questions about the universe's fate and the laws that govern it. The latest theories and experiments aimed at understanding dark energy are diverse, ranging from modifications of Einstein's theory of general relativity to innovative observational campaigns. One leading theoretical approach is the concept of quintessence, a dynamic field that changes over time and space, unlike the cosmological constant, which Einstein originally introduced to his equations of general relativity to allow for a static universe and later abandoned. Quintessence models suggest that the strength of dark energy could vary, providing a possible explanation for why the expansion of the universe is accelerating now after billions of years of deceleration following the Big Bang. Another area of exploration involves theories of modified gravity, which propose that the observed acceleration could be due to new aspects of gravity not accounted for in general relativity, especially over large scales. These theories challenge our fundamental understanding of gravity and require rigorous testing through observations. On the experimental front, several ambitious projects are underway to probe the nature of dark energy and its effects on the cosmos. The Dark Energy Survey, DES, using a powerful digital camera mounted on a telescope in Chile, has mapped millions of galaxies to study the structure of the universe over vast scales and time periods. By analyzing how clusters of galaxies have grown over time under the influence of dark energy, scientists hope to shed light on its properties. Similarly, the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, promises to provide unprecedented insights into dark energy. By surveying the sky in detail over 10 years, LSST aims to uncover the nature of dark energy by observing billions of galaxies and tracking how the universe's expansion has evolved. Another pioneering effort is the Euclid mission, a space telescope developed by the European Space Agency, scheduled for launch in the near future. Euclid is designed to map the geometry of the dark universe by measuring the distribution of galaxies and the bending of light, gravitational lensing, caused by dark matter and dark energy, offering clues about the underlying physics driving the universe's expansion. Gravitational lensing, a phenomenon predicted by Albert Einstein's general theory of relativity, has become an invaluable tool in the study of dark matter distribution across the universe. This phenomenon occurs when the gravitational field of a massive object, such as a galaxy or cluster of galaxies, warps the fabric of space-time around it, bending the path of light from a more distant object. This effect can magnify, distort, and even produce multiple images of the background object, depending on the alignment between the observer, the foreground mass, and the background light source. Gravitational lensing observations are particularly powerful for studying dark matter because dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopic observations. However, dark matter does exert gravitational forces, influencing the motion of stars within galaxies, the gas in galaxy clusters, and the path of light through the universe. By analyzing the light from distant galaxies and quasars that has been bent by intervening dark matter, astronomers can map the distribution and concentration of dark matter, even though it cannot be seen directly. There are two primary types of gravitational lensing: strong and weak. Strong lensing occurs when the foreground object is massive enough, and the alignment is such that it creates highly distorted or multiple images of the background object. Strong lensing can create striking phenomena such as Einstein rings, where a perfectly aligned lensing object produces a circular image of the light source. By studying these rings and multiple images, astronomers can directly map the mass distribution of the lensing object, revealing the presence and structure of dark matter. Weak lensing, though subtler, is more common and occurs when the distortion of background objects is slight. This form of lensing affects the shapes of numerous distant galaxies slightly, causing a coherent distortion pattern that can be detected statistically over large areas of the sky. By measuring the shape distortions of millions of galaxies, astronomers can create detailed maps of the dark matter distribution on large scales, revealing the cosmic web of dark matter that underlies the visible universe. Gravitational lensing has provided some of the most direct evidence for dark matter, confirming its existence and providing insights into its properties. For example, observations of colliding galaxy clusters, such as the Bullet Cluster, have used gravitational lensing to separately map the distribution of dark matter and ordinary matter. These observations have shown that dark matter interacts only through gravity, bypassing other forces that affect normal matter, a key piece of evidence supporting the dark matter hypothesis. The discovery of Oumuamua in October 2017 marked a milestone in astronomy and our understanding of the cosmos. As the first confirmed interstellar object to pass through our solar system, Oumuamua's appearance challenged our preconceptions and opened up new avenues for research into the composition, dynamics, and origins of objects from beyond our solar system. Oumuamua, which means scout or messenger in Hawaiian, was detected by the Pan-STARRS 1 telescope in Hawaii as it made its closest approach to the Sun. Its highly elongated shape, unusual for asteroids or comets within our solar system, and its unexpected acceleration as it passed through the solar system sparked intense interest and speculation among scientists. The significance of Oumuamua's discovery lies in several key areas. Interstellar visitors. Oumuamua confirmed that objects from other star systems can and do enter our solar system, providing direct evidence of material exchange between stars. This has implications for our understanding of planetary system formation and evolution, suggesting that the building blocks of planets, and potentially the precursors of life, could be exchanged between distant star systems. Composition and origins. Initial observations suggested Oumuamua was an asteroid, but its lack of a cometary tail as it approached the Sun puzzled astronomers. Later studies proposed it might be a new type of object, possibly a fragment from a disintegrated comet or even a piece of interstellar debris. Understanding Oumuamua's composition and origins could provide insights into the processes at work in other planetary systems and the diversity of objects formed in these distant environments. Oumuamua exhibited non-gravitational acceleration, changes in its speed and trajectory that couldn't be explained solely by the Sun's gravity. This led to various hypotheses, including outgassing, the release of gas from its surface, which is common in comets, but had not been directly observed in Oumuamua due to the lack of a visible coma or tail. This behavior has prompted discussions about the mechanisms that could cause such acceleration in interstellar objects. The discovery of 2I/Borisov in August 2019 by amateur astronomer Gennady Borisov marks another monumental step in our exploration of the cosmos, being the second interstellar object detected passing through our solar system and the first confirmed interstellar comet. Unlike Oumuamua, whose origins and classification sparked widespread debate among scientists, Borisov was readily identified as a comet due to its distinct cometary features, including a glowing coma and a tail, which are characteristic of comets as they approach the Sun and their icy bodies begin to sublimate. Borisov offered scientists a precious opportunity to study the material composition of an object from another planetary system. Observations revealed that Borisov's composition is remarkably similar to that of comets native to our solar system, suggesting that the processes forming comets may be universal. This insight is invaluable for understanding the building blocks of planetary systems and the distribution of water and organic molecules across the cosmos, elements that are essential for life as we know it. Borisov's trajectory confirmed its interstellar origin, entering our solar system with a hyperbolic orbit that indicated it was not gravitationally bound to the Sun. Its speed and path provided data on its approach and eventual exit from our solar system, contributing to our understanding of the dynamics of interstellar objects and the gravitational interactions within our solar system. Implications for planetary system formation. The discovery of Borisov, following closely after Oumuamua, suggests that interstellar objects passing through our solar system may be more common than previously thought. This reinforces the idea that the exchange of material between planetary systems in our galaxy could play a role in their evolution and possibly in the seeding of life-giving compounds across the galaxy. The observations of Borisov have underscored the need for continued vigilance and the development of technologies to detect and study interstellar visitors. With advancements in telescope technology and observation networks, astronomers hope to discover more interstellar objects, offering further insights into their origins, trajectories, and physical properties. Each new discovery allows us to piece together the larger puzzle of our universe's history and the processes that govern the formation and evolution of planetary systems. Hoag's object is a captivating and mysterious galaxy that stands out due to its unique and striking appearance. Classified as a ring galaxy, it features a nearly perfect circular ring of young, hot blue stars encircling a brighter, more compact yellow core of older stars. This rare configuration challenges our understanding of galactic structures and formation mechanisms, making Hoag's object a subject of intense study and fascination in astronomy. Discovered in 1950 by astronomer Arthur Hoag, who initially mistook it for a planetary nebula, further investigation revealed its true galactic nature. Located approximately 600 million light-years away, Hoag's object is one of the most well-defined examples of a ring galaxy, a type of galaxy that is relatively rare in the observable universe. The origin of Hoag's object's distinctive ring structure remains a topic of debate among astronomers. One leading theory suggests that it could have formed through a particular type of galactic collision and merger. In this scenario, a smaller galaxy might have passed through the center of a larger one, triggering a wave of star formation that eventually formed the ring. Alternatively, the ring could result from the galaxy's original disk, undergoing a unique form of instability that caused it to rearrange itself into the current ring-like pattern. What makes Hoag's object even more intriguing is the presence of a second, fainter ring detected outside the main ring, suggesting that this galaxy's history and formation are even more complex than previously thought. This outer ring contains faint, older stars and hints at possible periodic episodes of star formation or multiple galactic events that contributed to the galaxy's current structure. Zombie stars represent one of the cosmos's more peculiar and intriguing phenomena, challenging traditional understandings of stellar death and survival. In the celestial context, a zombie star refers to a stellar remnant that has survived a supernova explosion, an event typically considered the death throes of a star. This survival suggests a partial or failed supernova, wherein the star is not completely destroyed but instead leaves behind a core that continues to shine, a star that has come back from the dead, so to speak. The concept of zombie stars emerged from observations of certain supernovae that did not quite match the expected outcomes. One key example involves Type Ia supernovae, thermonuclear explosions of white dwarfs in binary systems. These events are crucial for measuring cosmic distances and have led to the discovery of the accelerating expansion of the universe. However, some observed supernovae are fainter than the standard Type Ia. suggesting that the white dwarf was not completely disrupted, but rather lost a significant portion of its mass in the explosion, leaving behind a smaller, damaged remnant. The existence of zombie stars has significant implications for our understanding of stellar evolution and the diversity of supernova mechanisms. For instance, it suggests that there is a range of outcomes for the final stages of stellar evolution, influenced by factors such as the star's mass, composition, and its interaction with companion stars in binary systems. This diversity challenges simple categorizations of stellar life cycles and highlights the complex physics governing supernovae. Studying zombie stars can provide insights into the conditions required for different types of supernova explosions and the processes that lead to partial stellar destruction. This research has implications for understanding nucleosynthesis, the creation of heavy elements in supernova explosions, as zombie stars may represent environments where these processes occur differently than in complete supernova. Furthermore, the study of zombie stars contributes to refining models of Type Ia supernovae, which are pivotal for cosmology. Since these supernovae serve as standard candles for measuring cosmic distances, understanding any deviations from the norm, such as those caused by zombie stars, is crucial for the accuracy of measurements that underpin our knowledge of the universe's expansion. KC 846285, also known as Tabby's star, has captured the imagination of astronomers and the public alike due to its mysterious and dramatic fluctuations in brightness. Located about 1,470 light-years from Earth in the constellation Cygnus, this star has exhibited irregular dimming events that have puzzled scientists since its discovery. Unlike anything observed in other stars, these dimming events have led to a wide range of theories and speculations regarding their cause. Tabby's star was first noticed by citizen scientists as part of the Planet Hunters project, which uses data from the Kepler Space Telescope to search for exoplanets by detecting dips in starlight caused by planets passing in front of their host stars. However, the light pattern of KIC 846285 was unusual. Its brightness dipped by up to 22%, and the events did not exhibit the regular patterns typically associated with planetary transits. Furthermore, the depth and irregularity of the dimming could not be easily explained by known natural phenomena. Several hypotheses have been proposed to explain the behavior of Tabby's star. One suggestion involves a swarm of comets or debris orbiting the star, which could occasionally block its light as seen from Earth. This could happen if, for example, a close pass of another star disturbed a comet belt, sending a large number of comets into orbits that take them in front of KIC 846285. However, the amount of material required to cause such significant dimming makes this scenario unlikely. Another theory posits that the dimming is caused by dust clouds resulting from the collision and breakup of asteroids or planets in the star's vicinity, creating a cloud of debris that occasionally obscures the star's light. This scenario could account for the irregularity of the dimming events, but would also imply a rare and coincidental timing for the observation of such an event. A more speculative and controversial hypothesis involves the possibility of an alien megastructure, such as a Dyson sphere constructed around the star to capture its energy for an advanced civilization. This idea, while intriguing, is considered highly unlikely by most scientists and is taken more as a testament to the mystery surrounding Tabby's star rather than a viable explanation. Hypervelocity stars, celestial sprinters of the galaxy, are stars moving at speeds so great they're able to escape the gravitational pull of the Milky Way. These stars traverse the galaxy at velocities exceeding hundreds of kilometers per second, far surpassing the speeds of typical stars in the Milky Way, including our Sun. The discovery and study of hypervelocity stars have provided astronomers with valuable insights into the dynamic processes at work in the galaxy and the powerful forces capable of propelling these stars to such extreme velocities. The existence of hypervelocity stars was first predicted theoretically, but the first such star was not observed until 2005. Since then, the advancement of observational technologies and methods has led to the identification of several more hypervelocity stars, each offering a unique perspective on the violent phenomena capable of accelerating stars to such high speeds. The predominant theory behind the origin of hypervelocity stars involves interactions with the supermassive black hole at the center of the Milky Way. According to this theory, a binary star system, two stars orbiting each other, wanders too close to the galaxy's central black hole. The intense gravitational forces exerted by the black hole can tear the binary apart, capturing one star while violently ejecting the other at a significant fraction of the speed of light. This slingshot effect propels the star out of the galaxy, sending it on a lonely journey through intergalactic space. Another scenario that could give rise to hypervelocity stars is the collision of multiple star systems, or the explosive supernova of a star in a binary system, where the resulting forces eject one of the stars at high velocity. While less common than interactions with the supermassive black hole, these events contribute to the diversity of hypervelocity stars observed. The study of hypervelocity stars has several important implications for astrophysics. Firstly, these stars serve as indirect probes of the environment near the galaxy's central supermassive black hole, offering insights into the dynamics and interactions in one of the most extreme environments in the universe. Additionally, the trajectories and velocities of hypervelocity stars can be used to map the gravitational potential of the Milky Way, contributing to our understanding of the galaxy's mass distribution, including its dark matter halo. Luminous red novae represent a rare and intriguing class of stellar explosions, distinguished by their distinctive red color, transient nature, and luminosity, which falls between that of classical novae and supernovae. These cosmic events have captured the interest of astronomers as they probe the complex processes of stellar evolution and interaction. LRNE are believed to result from the merger of two stars, a process that sets them apart from other types of stellar explosions. The scenario typically involves a binary star system where the stars are close enough that material from one star can be transferred to its companion, eventually leading to a merger. This merger process releases a significant amount of energy, leading to the luminous outburst characteristic of LRN, and ejects material into space, forming an expanding shell of gas and dust that gives the nova its red appearance. The study of LRNE offers valuable insights into the dynamics of binary star systems and the end stages of stellar evolution. The process leading to an LRN event may begin with a common envelope phase, where one star in a binary system expands into a red giant and engulfs its companion. The friction within the envelope causes the stars to spiral closer together, eventually leading to the merger. The energy released during the merger heats the ejected material, causing it to shine brightly and produce the observed red nova event. One of the most well-studied examples of a luminous red nova is V1309 Scorpii, which erupted in 2008. Prior observations of this system provided a rare and detailed pre-merger history, showing the orbital period of the binary system decreasing as the stars spiraled closer together. This event has become a key case study for understanding the nature and mechanics of LRN. LRNE contribute to our understanding of the diversity of transient astronomical events and the fate of binary star systems. They are also significant for understanding the synthesis of certain elements, as the conditions during the merger may allow for nucleosynthesis, contributing to the chemical enrichment of the interstellar medium. Magnetars are a fascinating and extreme subset of neutron stars, distinguished by their incredibly strong magnetic fields, among the most powerful known in the universe. Neutron stars themselves are the remnants of massive stars that have undergone supernova explosions, collapsing into incredibly dense objects roughly the size of a city, but containing more mass than the Sun. What sets magnetars apart is their magnetic field's intensity, which can be over 1,000 times stronger than that of a typical neutron star, reaching up to 1015 Gauss. Earth's magnetic field, for comparison, averages about 0.5 Gauss. The origin of magnetars' intense magnetic fields is still a subject of research, but it is believed that these fields are a result of the conservation of magnetic flux during the star's collapse. As the progenitor star collapses, its magnetic field lines are compressed into a smaller volume, dramatically increasing the field's strength. Magnetars are known for their violent and energetic behavior, emitting high-energy X-rays and gamma rays. They can produce giant flares and bursts of radiation so powerful that they can affect Earth's atmosphere and even temporarily alter its magnetic field despite being thousands of light years away. These emissions are thought to be caused by the instability and realignment of the magnetar's magnetic field, which can release a tremendous amount of energy. The discovery of magnetars has significantly contributed to our understanding of the universe's extreme conditions. Observing magnetars allows scientists to study the physics of matter under incredible densities and magnetic fields, testing the limits of physical theories. Magnetars have been linked to various astronomical phenomena, including some types of short gamma-ray bursts and anomalous X-ray pulsars, providing insights into the diverse outcomes of stellar evolution. Studying magnetars also has implications for the study of gravitational waves and the behavior of matter at nuclear densities. The extreme conditions around magnetars could reveal new physics about the state of matter in such extreme environments, potentially offering clues about the inner workings of atoms and subatomic particles under conditions unattainable in laboratories on Earth. Wolf-Rayet stars represent one of the later stages in the life of massive stars, showcasing some of the most dramatic and violent processes in stellar evolution. These stars are named after the French astronomers Charles Wolf and Georges Rayet, who first identified their unique spectral characteristics in 1867. Characterized by their incredibly strong stellar winds and the significant loss of their outer layers, Wolf-Rayet stars exhibit broad emission lines in their spectra, indicative of the presence of heavy elements such as carbon, nitrogen, and oxygen. The significance of Wolf-Rayet stars in the cosmos cannot be overstated. They are massive stars, typically more than 20 times the mass of the Sun, that have entered a phase of their life where they are losing mass at a remarkable rate, driven by the intense radiation pressure from within. This mass loss is a crucial aspect of their evolution, stripping away the outer hydrogen layers to expose the heavier elements in the core. This process enriches the interstellar medium with heavy elements, contributing to the galactic chemical evolution and providing the raw materials for future generations of stars and planetary systems. Wolf-Rayet stars are often found in regions of active star formation and can be considered precursors to supernovae, particularly type Ib and IC supernovae, which lack hydrogen lines in their spectra. The end of a Wolf-Rayet star's life is marked by a spectacular explosion, leaving behind either a neutron star or a black hole. In some cases, the core collapse of a Wolf-Rayet star is thought to produce long-duration gamma-ray bursts, the most energetic events in the universe, observable across vast cosmic distances. Continuing our journey to these unusual phenomena, we encounter Fermi bubbles. Fermi bubbles are enormous, balloon-shaped structures filled with high-energy particles that emanate from the Milky Way's core, extending outward for about 25,000 light-years above and below the galactic center. Discovered in 2010 through observations by NASA's Fermi Gamma-Ray Space Telescope, these mysterious bubbles glow in gamma-ray light, the highest energy form of light. The discovery of the Fermi bubbles has provided astronomers with crucial insights into the processes occurring at the Milky Way's heart and the history of our galaxy's evolution. The exact origin of the Fermi bubbles is still a subject of research and debate among astronomers. One prevailing theory suggests that they were formed by past eruptions from the supermassive black hole Sagittarius A*, located at the center of the Milky Way. These eruptions could have occurred millions of years ago when the black hole ingested a large amount of gas and dust, releasing a tremendous amount of energy that propelled particles at high speeds into space, forming the bubbles. Another hypothesis posits that the bubbles could result from intense episodes of star formation near the galactic center. In this scenario, massive stars would have exploded as supernovae, injecting energy into the surrounding space and driving the creation of the bubbles. These stellar explosions could also accelerate particles to nearly the speed of light, contributing to the gamma-ray emission observed. The study of Fermi bubbles is crucial for several reasons. Firstly, they act as a record of the Milky Way's energetic past, offering clues about the events that have shaped our galaxy's evolution. Understanding the mechanisms behind their formation and the energy sources powering them can provide insights into the behavior of supermassive black holes and the role of galactic nuclei in shaping galaxies. Furthermore, the particles within the Fermi bubbles are believed to be a source of cosmic rays, high-energy particles that travel through space at nearly the speed of light. Studying these particles can shed light on the processes that accelerate particles to such high energies, contributing to our broader understanding of cosmic rays' origins and their impact on the galaxy. Additionally, the Fermi bubbles are an example of the types of large-scale structures that can exist in galaxies, offering a comparative tool for understanding similar phenomena in other galaxies. Observations of other galaxies have revealed bubble-like features, suggesting that the processes observed in the Milky Way may be common in the universe. Moving on from Fermi bubbles, we discover wormholes. Rooted in the equations of Albert Einstein's general theory of relativity, wormholes suggest the possibility of connecting two distant points in space and time, potentially enabling travel over cosmic distances in much shorter times than light would take to travel in normal space. Theoretical physicist John Archibald Wheeler coined the term wormhole in the 1950s, but the idea itself traces back to a solution of Einstein's equations proposed by Einstein and Nathan Rosen in 1935, hence the name Einstein-Rosen bridges. These bridges were initially thought to connect two different regions of space-time, possibly even creating a bridge between two different universes. The most common depiction of a wormhole is as a tunnel with two ends, each at separate points in space-time, much like a tunnel with ends in different cities. The interior of the wormhole might be a region of space-time that allows a traveler to move from one end to the other faster than a light beam traveling outside the wormhole, though not actually exceeding the speed of light within the wormhole itself. Despite their theoretical underpinning, no empirical evidence exists to suggest that wormholes exist or could be used for space travel. One significant challenge is the stability of wormholes. Theoretical models suggest that the throat of a wormhole would naturally collapse so quickly that nothing could pass through from one end to the other. To keep a wormhole open, exotic matter with negative energy density would be required, something that has not been conclusively observed. This matter would counteract the wormhole's tendency to collapse, but whether sufficient exotic matter can exist, and whether it can be manipulated for this purpose, remains speculative. Moreover, even if wormholes could exist and be stabilized, navigating them poses additional challenges. There would be no guarantee of where or when the other end of the wormhole would open, making it a potentially risky proposition for anything other than theoretical exploration. The concept of wormholes has profound implications for our understanding of the universe and the nature of space-time. It challenges the conventional notions of distance and connectivity in the cosmos, suggesting that the fabric of the universe might be far more intricate and interconnected than previously imagined. Wormholes also raise fascinating possibilities for time travel, as they could theoretically allow for movement not just across space but through time. As we near the end of our journey through the vast expanses of astronomy and cosmology, it becomes evident how these scientific discoveries profoundly influence our philosophical understanding of existence and our place in the universe. The more we learn about the cosmos, the more our perspective on life and our role within this immense universe evolves, challenging us to rethink our notions of significance, identity, and unity. Recent discoveries, from the observation of gravitational waves to the imaging of a black hole's event horizon, not only expand our knowledge of the physical universe, but also invite deep reflections on the nature of reality itself. Gravitational waves, for instance, have confirmed a century-old prediction of Einstein's theory of general relativity, opening new avenues for understanding the universe's most cataclysmic events. This milestone underscores our interconnectedness with the cosmos, as we can now hear the ripples in the fabric of space-time created by distant astrophysical phenomena. The first image of a black hole's event horizon, a feat once thought to be impossible, has further pushed the boundaries of our imagination and scientific capability. Such an achievement not only provides direct evidence of these enigmatic objects, but also serves as a humbling reminder of the universe's vast mysteries waiting to be uncovered. It exemplifies our relentless pursuit of knowledge and the power of collective human endeavor in unraveling the cosmos's secrets. The exploration of exoplanets and the search for extraterrestrial life have significantly impacted our philosophical perspectives on existence. Discovering worlds orbiting distant stars in habitable zones where life as we know it could exist challenges our sense of uniqueness and prompts us to ponder the possibilities of life beyond Earth. This search broadens our understanding of life's potential diversity and resilience, emphasizing that we may just be one expression of life in a universe teeming with possibilities. The concept of the multiverse, suggested by certain cosmological theories, proposes that our universe might be just one of many, each with its own laws of physics. While still highly speculative, this idea has profound implications for our philosophical outlook, questioning the very nature of reality and our place within it. It challenges the notion of a singular universe and invites us to consider a much larger and even more diverse cosmic landscape than previously imagined. What fascinating mysteries do you believe exist in the universe? From the enigmatic dark matter and dark energy that seem to govern the cosmic structure and expansion, to the tantalizing prospect of parallel universes and the mysteries of black holes, where the known laws of physics converge and diverge in unpredictable ways, our quest for understanding is far from over. Each discovery peels back a layer, revealing not just answers, but a multitude of new questions, each more intriguing than the last. Let us know your thoughts and ideas in the comments below.